Moet ik inleiden? Welcome, everybody. It's a pleasure to introduce Rene Oudmaijer. A long time ago, we were together PhD students, but that's in the last century. Since then, I think he made a postdoc...
in Imperial College in London?
Yes, in London. And then he went to Leeds, where he became professor in astrophysics. But now he returned not to the Netherlands, but to Belgium. And he is now part of the Royal Observatory, where he is also responsible for outreach and the calendar.
Yeah, absolutely.
So it's a pleasure to welcome Rene. And well, I look forward to his work on Herbig Ae BE stars.
Thank you very much.
Please.
Thank you very much, Hans. It's a pleasure to be here in Leuven. So yeah, when I thought about it, my first foreign trip as a PhD student was to Leuven. And I think I was a PhD student for a month, and then I met Hans already. It was on post-HB stars and abundances. And there was a talk by Hans last week at the conference that I was. It was about abundances as well, but a lot of progress was made. And yeah, so I've been for exactly 25 years in Leeds, and since last month I'm working at the KSB, and one of my duties is communication information, and the letter that I signed yesterday was to the police in a place somewhere in Belgium to tell them when it was dark, when there was sunset in that particular place in 2018. So they were investigating a car crash, and they wanted to know about the conditions there. So there you go. Okay, so, but today what I'd like to talk to you about is a long-running project that I've been doing on Herbig Ae BE stars. These are young pre-main sequence stars, and I've got a cast of thousands that have been working with me on this, and what I'm going to summarize really in the next 40, 50 minutes is the work of 4 of my PhD students in the last decade. Let me just show them here. So I'm going to talk about John Fairlamp, Michael Vioke, Karen Ababakar, and Chumpon. And they all went for the first postdoc in Leeds, either to Hawaii, or to Chile, or to Iraq, or to Bangkok. And I think that means that they were really glad to get rid of me. So what I'm going to talk about is I'll give you a little bit of an introduction on young stars, pre-main sequence evolution. And I will concentrate on the accretion onto these stars via accretion disks, and I'll give you some of the latest results that we got with Gaia. And then we ventured a little bit into machine learning. I was always a little bit skeptical, but I hope to convince you that it actually works. So there you go. I hope perhaps you knew that already, but I was happily surprised. Now then, let me first concentrate my 3rd-year course in star and planet formation. It's an entire module running over an entire semester. Let's just do this in one slide. So stars are formed in molecular clouds, okay? And at some point, gravity overcomes the pressure, and the cloud collapses, and it gets denser, it gets denser, it gets hotter and hotter and denser, and at some point, nuclear fusion starts. The star is born, okay? The one addition to the story is that these clouds, they rotate a little bit beforehand. And if you shrink a cloud, then it starts to spin faster, and if you've got something that's spinning fast, it basically will extend in the equatorial plane, just like when you spin a pizza, okay? And the net effect is that you start with a cloud, it gets denser and a little bit warmer. You can see it at millimeter wavelengths in this case. Then after the disk is being formed, also automatically a jet is emanating from the system. And what you can see then is a so-called class 1 object that you can see in the far infrared, mid-infrared. You see the emission from a much warmer body than here. At some point, the molecular cloud disperses. You end up with a disk and a jet system, which you then can observe essentially in the infrared and longer wavelengths. Then we don't have any material to accrete anymore. We end up with a disk and probably some protoplanets in it, and resulting in a planetary system. Okay. Now, this takes only a few million years in the case of a solar mass star. And I find it remarkable how quickly this is, huh? Because if you think about a pregnancy, that's about 9 months, that's about 1% of a human life. Well, if I look at a few million years on the lifetime of a few billion years, you can see that basically the birth of a star is just like this, blink of an eye. This graph was actually made by Abigail Frost, who many of you may know already. And here, this is basically where I'm going to concentrate on, the pre-main sequence objects, the objects where we still don't have fusion in the core, and the systems are basically stars surrounded by a disk. Sometimes there's a jet emanating from them. And it's nice, actually, that we can nowadays observe these systems, typically with ALMA at high resolution. And here I've got a couple of systems observed by Nienke van der Marel. And you can see that this cartoon that was actually older than these observations still had the same color scheme. Shows you these gaps in these disks as well. We don't know yet whether that's really carved by a planet or due to some other process, but it's very tempting to believe that it's actually a planet that was responsible for these gaps. Okay, so that's setting the stage. And let's put them now in an HR diagram. And here I've got one from Alessian and Willebrun, where you've got temperatures from a few thousand Kelvin to 10,000 Kelvin, and luminosities from less than a solar luminosity to in this case, 100. And here we've got evolutionary tracks. They are different from the most of the ones that you see, which will be post-main sequence tracks. These are pre-main sequence tracks. Stars shrink and contract, and then move to the main sequence. This is the 4 solar mass curve. I forgot which one is the 1 solar mass curve. Let's say it's this one. What's relevant here is that the structure of the stars is different as a function of mass. If I'm looking here, the outer parts of the stars are convective, just like the sun. So there's these bubbles of gas, ionized gas that are moving about, and these stars, they are radiative. You don't have any convection cells. The net effect is that if you've got convection, you've got moving charges, you induce a magnetic field in these objects. So the expectation already is that these lower mass stars and the cooler stars are magnetic, and the higher mass stars are not, okay? And that's indeed what we see. The bottom line of this graph is the bigger the symbols, the stronger the magnetic field. And that's what we find. The strongest magnetic fields are indeed where the stars are magnetic. Some of these objects are magnetic, which is a little bit of a conundrum, okay? Now that we've got this HR diagram, typically here I'm looking at what people would call T Tauri stars. These are stars like the sun, basically they become the sun, solar mass stars that are pre-main sequence. Here we've got more massive objects that are called Herbig Ae Be stars, named after Herbig, right? He was looking for young pre-main sequence stars in 1960, so 60 years ago. And he wanted to look at more massive stars, so he decided to look at spectral types A and B. He expected there would be some material around it, so he looked at emission lines as well, so AE, BE. And something that has received a little bit more attention in recent years is the gap between the T Tauri stars. There's an entire community working on T Tauri stars, and there's a community, smaller one, working on Herbig stars, and there's this gap in between that people have only really started studying recently, and we call them intermediate mass T Tauri stars. They are a little bit more massive than the T Tauri stars and less massive than the Herbig stars, okay? Now, and today I'm going to concentrate a little bit more on the Herbig stars. Let's give you a little bit of a rundown of these things. I think it's fair to say that most, if not all, Herbig stars are in binaries, okay? That's really quite a surprise. So I grew up, and Hans grew up, and other people in this room grew up, that single stars are the begin all and end all of stellar evolution, but we have to worry about binaries now. It started in 2006 when I was with Debbie Baines, and we had this very clever technique to probe very small scales around Herbig stars to look for the disks. and the only thing we found were binaries. So 70% of these were in binaries. There's a big study that started in 2005, but was only published in 2023 by Thomas et al., where they looked at AO-assisted imaging, and from these images in the K-band, they found that many objects are in binaries too. Some of them are actually in triples, okay? And together with Jonathan Dodd, a PhD student in Leeds, we are using Gaia to look for binaries, to basically astrometrically, we try to reveal the presence of binaries. And we found out of more than 300 objects that include the T Tauri stars, that most of them are in binaries too. And if you combine all these studies, you find that 74% of Herbig stars are in binaries. And this is observed, so that's a lower limit. So far, we don't really see a trend with mass. I'm not going to go into detail here, but it might not be necessarily what you would expect, because you would expect that the earlier type stars are more massive and that they would be more likely to be in binaries. Now, one of the things that we try to work out is whether these lower mass, later type stars are actually the higher mass objects in the sample. We still have to look at that. Okay, that's one thing. Herbig stars are also suggested to host planets. There's a very famous picture from many years ago where this object, HD 100546, had a couple of blobs that turned out to be moving. And they were suggested to be planets, but it's now a little bit more controversial. I think there's only one Herbig star that people are really agreeing that they're surrounded by, that they're orbited by a planet. But when you're looking at the high-resolution imaging of Herbig stars, we find that many of them, and this graph, I think in the review by Britton et al., these were the best pictures available. I think it's even better now. Half of them have spiral structures. And it's very hard to get a spiral structure without the intervention of a planet, for example. So often people use this as indirect evidence that planets are being formed at the Herbig Ae Be stage. Where do they fit in the HR diagram and in the grand scheme of things? I think it's fair to say that the T Tauri stars, they are the ones, the stars that become like the sun. They're magnetic, as I told you from the convection. And we also know how they accrete their mass. They are surrounded by a disk, and via the field lines, material is basically being dumped onto the star. We had the Northern Lights a few weeks ago in Belgium, even visible in Belgium, and it's essentially charged particles from the sun are entering the magnetic field of the Earth, follow the field lines, and are being dumped on both the North and the South Pole. Exactly the same thing happens in these objects. Then, on the other end of the scale, we've got very massive stars, the ones that go boom, become a supernova. Very many open questions about these objects. We don't know really how massive stars form. And from an observational point of view, it's very difficult to do that, to study them, because they're so massive, they're still embedded in the molecular clouds. You can't see them in the optical. We really have to go to infrared wavelengths. And in Leeds, we started a big project to catalog all these objects and study them. And the nice thing is that the Herbig stars are in between the two. They basically form the link between the low mass stars and the high mass stars. So we can see them in the optical, as I just told you. And that means that we've got many more ways of studying them than in more massive stars. So on the one hand, I expect Herbig stars to be forming like T Tauri stars, because the lowest mass Herbig stars will be like them, and the highest mass will basically act as a proxy to study the most massive ones. And here, when we had Gaia DR2, Miguel Villoca produced this graph on the day of the data release 2, and put all the then known Herbig stars in the HR diagram. And just for the record, this is the graph that I just showed you. Okay, so it's extending to much higher masses. Okay. Now then, one of the questions that I'd like to address today is, how do these stars, they're still pre-main sequence, they still accrete material, they still grow to higher masses. And for the low mass stars, I already indicated it a little bit, we essentially know what happens. We've got the star, we've got these magnetic field lines, we've got a disk that's basically the material is falling in, because if you lose angular momentum, there's only one way, and that's going towards a star. You can't cross the field lines, so this is what we call magnetically controlled accretion. Now, I just told you already that the higher mass stars don't have a magnetic field, and in a way, we don't know what happens, okay? So that's interesting to study. Having said that, about 10% of all A stars, normal A stars, are found to have a magnetic field. And indeed, about 10% of all Herbig Ae stars are found to have a magnetic field. So there is something going on. We don't know whether that magnetic field is generated inside the star, or whether it's the remnant of when it had a magnetic field, it turned off making a magnetic field, but at some point it has to dissipate. So it could be a fossil field, okay? But the bottom line is for 90% of the stars, I definitely would not expect magnetospherically controlled accretion. So how do we want to study that? How can we study this? And I think one way of trying to do this is to look very close to the stars. If you're interested in mass loss from stars, you want to be very close to the stellar surface. If you're interested in mass accretion, you want to be very close to the stellar surface as well. And we employed a trick called spectropolarimetry to do so, okay? The idea is the following. If I have a star, then it's shining light and it's basically going towards you. The light will not be polarized, okay? Well, perhaps there might be some interstellar dust. But if I have material surrounding that star, then if light is being scattered and moving towards you, it will be polarized. Just like the light, if you go to the beach, that the light that's scattered off the sea is polarized, and you can get rid of it by putting on polarized sunglasses, okay? Now, the scattering by the sunlight on the sea is a little bit different, but imagine now that I've got ionized gas around the star. The free electrons can scatter light towards you. And as a result, the light will be polarized. So imagine now I've got an electron here, light from the star hits this, then it will be polarized in this direction. If it's here, it will be polarized in this direction, okay? Hang on. If it's going here, it will be polarized in this direction. And here it will be polarized in this direction. That would actually make life a little bit complicated, because if light is polarized like this, like this, like this, like this, the net polarization is 0. So if I scatter around something that's by something that's round on the sky, I will have a net 0 polarization. However, if I have an edge on disk, then light will be polarized like this, and I end up with a net polarization. So far, so good? Now, that doesn't tell you too much yet, but if I would look at a star that has an emission line, then H alpha, for example, would be formed much further in the disk than where the starlight is coming from. So the H alpha line emission will be less polarized than the star. And if I find the difference in polarization between the continuum and the emission line, I can say, hang on, there must be some sort of disky structure around that star. And that was actually first applied to BE stars in the 70s. Now we know that BE stars are surrounded by a disk. But 50 years ago, that was very contentious, but this was one of the first ways that people actually found there were disks. So why am I telling you all this? Well, if I'm looking at a normal BE star, so a star surrounded by a disk, then the H alpha line would be something like, you've got continuum, you've got H alpha emission, and continuum. If I would take the polarization here, the continuum would be polarized, and I would have a dip across the H alpha line. And that's essentially a line effect in the spectropolarimetry Took me a few years that I could pronounce this without any problems. And this is the position angle. It essentially tells you the angle of the disk on the sky. But it turns out that if I'm looking at a T Tauri star, the structure is a little bit different. I've got a disk, I've got these accretion funnels, and if you look at the most simplified situation, you know from a T Tauri star that you've got H alpha emission, but you can actually also have the depolarization across the line, but the flip in the position angle. Okay, it's got to do with breaking symmetry, but just believe me that this is what you get if you put in the models. This is another way of showing polarization data in QU space. These are the Stokes vectors, but it's not relevant here. So the bottom line is, if I've got a star with a disk, I have a depolarization and nothing here. And if I've got something like magnetospheric accretion, I will have a flip. And then we thought, okay, let's test this. Let's go out and take data. Now, turns out that you need a signal to noise of about 1,000 to do this. So you have to have a lot of observing time. And especially when you're me, and you go to Australia, and you've got beautiful views of lightning, but no data, okay? But we did manage to get some data. And what we found, and so this is signal to noise of 1,000. Here's an object. This is a B-type Herbig star. The emission, just like the doctor ordered. I do have a depolarization, and the position angle is more or less flat. If I'm looking at the T Tauri star, I've got H alpha emission, and I've got the flip in both the position angle and the polarization. Essentially, I could have shown you the QU plane. It has a circle in the QU space. So here I find that the B-type object just has a disk, and a T Tauri star has some signature of this magnetospheric accretion of hotspots. And the big surprise was that these Herbig Ae stars also look like a T Tauri star. And these A stars, just like I showed you in the HI diagram earlier, they're not supposed to have a magnetic field. Not at all. But we found that most A stars behave like a T Tauri star. Okay, well, this is only 3, but took us a while, but we managed to look at all Herbig stars that you can do with all the telescopes in the world. It's about 57 of them. And here we've got spectral types. This is T Tauri stars, A types, and B types. And you can see the blue is the depolarization, and the red is the line polarization. Okay, so we can see there's actually quite a clear break, as clear as you can hope for, that's around the B7, B8 type temperature, or around 3 solar masses. So whatever happens, whatever is responsible for accretion onto a star, looks like there's a break at around 3 solar masses. Okay, so that's exhibit number 1, and I think we were the first ones back in 2000 something to actually demonstrate this. Now then we thought, okay, perhaps we can study the accretion in a different way as well. Perhaps we can look at the accretion rates. And what we did, we got actuator data of a lot of Herbig stars. This was really, I think, in the very first semester that actuator was on the telescope back in, I think, 2010 or something like that. We got data for 90 of these objects. What we said, okay, let's just do a proper job. We determine the stellar properties of these guys. We measure H alpha, we measure the extinction, see what we get, okay? And just briefly, we could fit most of the spectra very well with Kurit's models, determining the parameters, okay? Sometimes the emission is so strong that you're a little bit scuppered, but in most cases we managed to do so. And then there was a way of actually measuring the accretion luminosity, okay? And I hope that I'm allowed to drop something on the floor here. I am going to do it. So essentially, I already mentioned that material is basically falling onto these stars via these field lines, okay? And you can well imagine that if I drop this chalk from 1 centimeter, there's not a lot of noises there. I'm going to do it. And if I drop it from a little bit higher, I think it will be a bit noisier. It might even break, okay? Yeah, that was a little bit higher, louder. And essentially, you can work out for that material that's falling onto a star, the energy will be so high, it will be basically radiated at UV wavelengths, okay? So what you expect is an ultraviolet excess when you look at the spectral energy distribution of these stars. And here I'm looking at one of these X-shooter data. This is a model, and this is the observed data. You've got the emission lines, and you've got a distinct ultraviolet excess. And then you can link the ultraviolet excess, you can work out how much energy is being radiated, and you get yourself a luminosity, okay? And when we're looking at this luminosity, we actually find that there's a correlation between the luminosity of the star and the accretion luminosity over a wide range of objects. Here I'm looking at Herbig stars, I'm looking at T Tauri stars, and I think we even go into the realm of brown dwarfs, okay? Which is actually quite an interesting finding in its own right. But I'm interested in the accretion rate. But for the accretion rate, I need to link the luminosity to something else. And the gravitational potential energy depends on the mass and on the distance, right? So I need to do that. Oh, no, I'm skipping this one. So I need to do that. I can get the mass and the radius of a star if I know the location in the HR diagram. So give me a luminosity, give me a mass and a radius, I can give you the accretion rate, how much material is being dumped onto the star. We couldn't really do this in 2015, but we could do this in 2020 when we had distances to most of the Herbig stars. And yeah, that's what I've got here. Now, so our goal was actually to get the accretion rates, but there were a couple of other things that we could study with the Gaia data as well. And here I'm going to show you some things because I am interested in the properties of Herbig stars as a function of their mass. And here I'm looking at the infrared excess of these objects as a function of mass. The infrared excess, you can basically, you look the objects up in WISE, in the WISE catalog, and you can work out, okay? Turns out that the lower mass objects have much more dust around them, relatively speaking, than the higher mass objects. This was known before, but only for about 10 objects, believe it or not, okay? But we see that if you want to give a number to it, it's around 7 solar masses or so. You've got much less infrared excess than for lower mass objects. We actually think it has nothing to do with the accretion rate, but this is where you've got much more ultraviolet emission, and you can actually evaporate this circumstellar dust and just get rid of it, okay? Which makes it difficult, by the way, to form planets. If you don't have a disk and dust, you can't get any planets. Gaia DR2 did not tell you whether an object was photometrically variable, but we could play around a little bit with the error bars and define our own variability index. And we find that the lower mass objects are more likely to be variable than the higher mass objects. It's more or less the same break, which is not inconsistent with the idea that if you've got a star that is surrounded by an inhomogeneous disk, sometimes the light is a little bit blocked by the dust in the disk, and then it isn't. So variability could be related to the presence of a dusty disk. But it should, of course, be an edge-on disk, otherwise you're in trouble. And indeed, 25% of all the Herbig stars are variable, which is consistent with an opening angle of about 20 degrees for such a disk. Okay? And what is more, when we looked at the H-alpha profiles then we found that most of the objects that are variable are edge-on because the H-alpha profiles are doubly peaked. So what I just told you, perhaps I've got a dusty disk, must be edge-on, is arguably validated by the fact that they seem to be edge-on because the H-alpha profile is double peaked. That relates to something that's called the OXO phenomenon, where people already knew of a couple of objects that behaved very weirdly in that sense. But in a sense, we more than doubled the sample of these objects. Okay, but I think the bottom line is the lower mass objects have dust, the higher mass don't have it because it's probably evaporated. But now the accretion rate. I told you if you know the position in the H diagram, you know the luminosity, the accretion luminosity, then put in the mass and the radius and you can work out the mass accretion rate. And in the end we could pull this off for roughly 100 objects. And here I've got the H diagram again. Red, in this case, is low mass, a low accretion rate. Blue is a higher accretion rate, and you can see that the lower mass objects have a lower accretion rate than higher mass. Perhaps that makes sense, because if you want to be a higher mass object, you probably need to accrete more material, right? But what we're interested now in is there perhaps an evolution in accretion rate? Can we essentially get some other physical information from this? And if I would simply put the mass accretion rate that we measure as a function of h, I find that the older the objects become, the lower the mass accretion rate. And this is a graph, or a similar graph, has appeared in the past before. And it's totally wrong. And I honestly don't understand why people did it, but I tell you why, what happens. This is the H diagram. The low accretion rates are for the lower mass objects. The high accretion rates for the higher mass objects. But just like post-HEB evolutionary tracks, lower mass objects evolve slower than higher mass ones. So the higher mass ones are also the youngest. And the lowest mass ones are also the highest age ones, the oldest. So this graph, I don't know, are we looking at the evolution of an accretion rate or just at the mass effect, right? So what we did, we tried to really narrow down different parts of the H diagram to see whether we could actually get rid of that effect. And the best we could do was to look at different mass ranges, 2 to 2.4 solar masses, 2.6 to 2.9. And yeah, this looks like a scatter plot. This was about the best we could come up with. And we worked out that the accretion rate goes with h to the power -2. This happens to be totally consistent with the idea of a viscous disk. So what Hartmann did in 1998, he said, I've got a star, I've got a disk, it's a little bit viscous. By definition, material in the inner parts will lose angular momentum and will accrete onto the star. And this is the time dependence they found. So, in a way, we were quite pleased that we found this, right? It's always good to say that you validate a theory. But let's now have another look. I'm looking at a very small range in both age and mass. And here we can try to look at the intermediate mass T Tauri stars. I didn't really include them in the previous graph because we didn't look for them. But Sean Britton, he did. And he made the same graph, but with a different color scheme. Now blue is small accretion rates and red is high accretion rates. And instead of just looking at this very small part in the H diagram, we now compare the intermediate mass T Tauri stars with their Herbig counterparts. And you can see, hopefully from the colors already, there's a big change. And instead of having an accretion rate that might be decreasing a little bit, which is totally consistent with viscosity in a disk, it turns out that now that we have this larger baseline, we have a big increase in mass accretion rate. We've been looking at the left, right, and center. We cannot change this effect. And It took a while before we realized that. But when you look at anything stars with disks, and most papers in the literature, they don't really take into account the evolution of the star. Sometimes they do. They say the star gets hotter, so the dust gets hotter. But they never look at the disk itself. But you can imagine, perhaps, if I've got a cool star, has a neutral disk. If I've got a hot star, it's got an ionized disk. But the effect of the ionization actually results in a higher viscosity and hence a larger accretion rate. So that's a nice explanation that had never been taken into account. But the big surprise that we had is it's increasing, but it also solves a little bit of a conundrum, a problem that we had earlier, because people always said that we need too high an accretion disk, too massive a disk to explain these high accretion rates. Because this is high, but that means that in the past they were even higher. And that means that you really need to start with a fat disk. But now we can start with a much lower mass accretion rate. And that solves quite a few problems. So we submitted this, so let's, I hope I convinced you, and if you're the referee, then just say yes. Okay. Let's have a look at the accretion rates. I just mentioned the age, but let's now have a look at the mass. And if I plot the accretion rate as a function of mass of the stars, then I hope you can see it, that the low mass stars, there's a little bit of a steeper dependence than for the higher mass stars, okay? And I can actually play around statistically and fit lines here, starting from here and starting from there, and then I can actually find actually a kink in the accretion rate as a function of mass, which is about 4 solar masses. So this is independent of what I just showed you with the spectropolarimetry, but from a statistical basis, this is about the best value we can find. Now, we had, apart from the spectropolarimetry, quite a few studies looking at different things, at H-alpha variability, for example, at the sizes of hotspots, at the UV excess, that there was something different between A and B stars, okay? And I think it's fair to say that Herbig Ae stars, they really show a lot of evidence for magnetic fields, magnetospheric accretion, and different properties for the higher mass stars. And then the other surprise is that no one in the literature actually has from a theoretical perspective, wondered how material is actually accreting onto these hot stars. Okay? If you look in the literature, at some point people talk about something like boundary layer. Essentially, it's a disk that's shrinking, and if a disk is rotating Keplerian, it's actually rotating quicker than a star. So if it wants to fall into the star, it needs a lot of lose a lot of kinetic energy that can be radiated away. This boundary layer is known for white dwarf accretion and other things, but it hasn't been yet applied to Herbig stars, but it seems to be the best bet that we have. So I think the next step is now to how can we accrete material on these hotter stars. We think we know how to do it on the lower mass stars, but the challenge is now, can we do it for the hotter stars? I've got some ideas how to do it theoretically. I mean, you start with a star with a big magnetic field, and then you just make it smaller and smaller and smaller, and then you just see what the hydrodynamics tells you. Okay, so that's the first part of the talk. The second part of the talk will be a little bit smaller, but all the Herbig stars I've been talking about, it started with Herbig. Then there were some other people, they found an object, they thought, what could it be? Oh, it's not a post-HEB star, it's not a it could be a Herbig star. So it's quite a heterogeneous sample. And if you've got a inhomogeneous, heterogeneous sample, then it's nice to have a statistical result, but you always have that nagging doubt, could it be a selection effect, okay? So the next step that we wanted to do is to create our own sample of Herbig stars where we know what's going on and see whether this still holds. And that's where the machine learning comes in, okay? And what we said is, okay, what makes a Herbig star different from other stars? Well, it's got an infrared excess. It's got H alpha emission. And it's variable photometrically, okay? So perhaps if I look at 100,000 random objects, I just pick the ones that look like a Herbig star. Or I could do it for 1 billion objects. But that's a little bit of a big job, isn't it? And that's, of course, where machine learning comes in. And what we did is, okay, for the infrared access, let's take objects from the Allwise catalog, millions of objects. For the H alpha mission, let's look at some H alpha surveys of the sky, millions of objects. And for the photometric variability, let's use our little trick that we had from the Gaia data and look at the billions of objects there. So we've got data from Allwise, IvS and VVS. This stands for INT, photometric H alpha survey. And I think the V stands for Vista, I believe, in the south. So basically, we got 4 million objects that were observed basically in all these 3 catalogs. Okay, and then we want to know how pre-main sequence stars and Herbig stars look like. So we had a huge sample of pre-main sequence stars, and one of the things that is quite difficult sometimes is to know the difference between a BE stars and Herbig star. So we also collected a couple of classical B stars. And then we just got 400 random sources, and we fed this as a training set to the computer. We said, this is how the Herbig stars look like, these are the data. This is how BE stars look like with these data, and here you've got some random sources. And then let it crunch and just give us a probability of what you think this star looks like from these 4 million. And then they came up with this one, this graph. Here, this is the probability it's pre-main sequence, 0, 1. This is the probability it's a BE star, 0, 1. And 4 million objects are neither. Okay, so these are the normal stars. A bunch of objects has a very high probability of being a Herbig star, and a bunch of objects has a very high probability of a BE star. Nice. I can walk away now and say I've got all these candidates, but let's see whether this makes sense. Well, first of all, 80% of the pre-main sequence stars we fed it were returned as a pre-main sequence star by the network, and 85 of the BE stars. So that gives you a little bit of hope. Okay, you've got 15 to 20% contamination, but that's better than just looking at all these 4 million objects yourself. The other thing is that we found that the Herbig stars, the pre-main sequence stars, were much more likely to be clustered, they are the white circles, than the BE stars, which are typically field stars. And here's another one. So in the grayscale, it's the clusters, and the blue dots are the BE stars. So there's a very big difference. Happy meeting. There's a very big difference in the space properties. And we didn't tell the machine, the computer, anything about the space distribution, right? Another thing, the training set, and in the HR diagram, the red dots are the pre-main sequence stars, and the purple ones are the BE stars. Well, the BE stars, fair enough, are the bluest and the brightest. And when I'm looking at the classical BE candidates, the ones that had so the probability, the blue ones are 90%, so these are the ones that have a more than 50% chance of being a BE star. They are in the same location in the HR diagram. And note, I didn't say anything about distances to the computer, right? So that seems to work. Again, for the pre-main sequence candidates, they are all over the HR diagram. So they are here. And you notice they are a little bit above the main sequence, which you would expect for a pre-main sequence star, right? And here as well. And you can see that a large chunk is very bright. And the brightnesses in this HR diagram are really lower limits because we don't know properly the extinction. So they can even be brighter. So automatically, we already got 2,000 objects that could be a Herbig star. That's a factor of 5 to 10 more than we had already. Okay. At this moment, I started to become a little bit convinced. But let's just check. And what we did was we went observing. We got data on, we got observing time various telescopes just to take spectra, okay? And what happened is that, how shall I say this? Oh, here's an example. This was a BE star candidate, and the spectral type is actually B, and it's got emission. It's BE. Doesn't tell you that's a BE star, but it turns out that all the BE candidates, according to the machine learning, turn out to be a B star with emission. And from the pre-main sequence stars, essentially, they were all, we selected them to be the brighter ones, almost all the spectral types were A or B, and almost all of them had emission. That doesn't prove you yet, of course, that it's a pre-main sequence star, but it could have been an F star, it could have been an M star, could have been a Wolf-Rayet star. But the BE candidates all were B stars with emission, and the ones that we selected to be a Herbig Ae BE candidate turned out to be an A, E, or a BE star. And that's quite a success, I think. 14 out of 14. The ones that we thought were contaminants, 7 turned out to be indeed contaminants. One of them was an AGB star. And if I put now these objects, now that I got the spectral types, I even know the extinction properly, and I can put them in the HO diagram. And we can look at it and be happy that I was that. And we thought, okay, let's now see how we the final result. So we got 128 new Herbig stars. We got a couple of new T Tauri stars. We increased, especially the more massive Herbig stars, the number of objects, but that was a little bit of a bias because we looked at the brightest ones. Okay, but it's nice to actually have a little bit more Herbig B stars than A stars. And then we quickly looked at the infrared excess as a function of mass. This is a much prettier picture than I showed you in the beginning, but there seems to be really a big break at around 7 solar masses. And this is with the new objects. And when we look at the accretion rates as a function of the mass, and we do the same trick, we indeed find the same break at 4 solar masses. So that's the good news in a way, that the statistical result I showed you with the existing samples of Herbig stars still holds with a properly defined sample. And that's basically the story I wanted to tell you about what I've done with these PhD students who immediately fled the continent to be as far away from me as possible. I hope that you got a little bit of a feeling about Herbig Ae B stars, and that are actually quite useful objects to study, if only to just learn about the formation of massive and low mass stars. The big surprise, the big takeaway is that the magnetospheric accretion is actually extending to much higher masses and luminosities than previously thought. And one of the things I didn't highlight today, but these stars, they have evidence for planets, but these planets are being formed whilst the stars are still accreting. It's really a mess if we want to understand planet formation. And I'm really looking forward to looking at doing some more studies on boundary layer accretion around these objects. And that's what I wanted to share with you today, so thank you. Any questions? I can happily go through the room. If you just ask a question, I'll repeat it.
Okay.
Okay.
It's going to be a post-HB question.
Sadly, Cleo, it's not going to be a post-HB question. Yeah, I know. No, but I was wondering when you talked about the trend of accretion rate with age, and actually that you might expect an increase due to the ionization effects.
Yeah.
Is that simply due to the fact that if you have more ionization, your magnetic turbulence becomes stronger, or what is the
Yeah,
theoretical?
yeah. I didn't. I only said that the viscosity increased, but it's essentially MRI instabilities that do that for you. Yeah. So in the paper, we just used a toy model and didn't even talk about. I don't think we even mentioned MRI, but we said, well, if it increases with UV excess, then this is what happens. But yeah.
Makes sense.
Thank you.
I have a question about the binary plot you showed, that Herbig stars, a lot of them are in binaries.
Yeah.
Do we know what kind of periods these binaries are in?
Yeah. Why am I doing this? I'm going to show a plot and then I'm going to say no. But yeah, let me just. Yeah. Okay. So you can see already that if you look at objects that are 1-2 arc seconds away, these will be quite long periods, right? What Jonathan did in his paper with the Gaia data that we have, I think we can retrieve binaries between 0.2 and about 1 arc second. And because we know the distances to these objects, you can have some sort of idea about the separation distribution. There's a lot of hand waving. It seems to be flattish, Opic's law. But the shorter periods, there's not many data of Herbig stars where people look at radial velocity variations. Basically because it's not very easy to get these radial velocity variations in stars that are A, hot and have these broad absorption lines, and B, are active and have all these emission that is both variable and messing up your spectrum. Hopefully that answers your question a little bit.
So I was basically wondering, so you have the spectral type on the x-axis, and there are similar plots for main sequence stars with spectral type and the binary fraction. So I was wondering what happens between these two phases.
Yeah, yeah, I should have put it in. So Jonathan also made an H diagram where he color-coded the binarity. But I think the bottom line is that in the range that we're looking at, we do not find a correlation between the binary fraction with mass, luminosity, or even age. When I find this big difference between the intermediate mass T Tauri stars and Herbig stars for the accretion rate. If I look at exactly the same samples for binarity, flat, within the error bars.
Okay. And final question, does this affect your other studies about, say, the infrared excess or the variability and so on? Does binarity, I mean, when you place a star on the HR diagram, how careful do you have to be?
Yeah, good question again. I don't have a ready, well, let's look at this guy. These stars are too far away to really affect much. And I believe we looked at binarity and the infrared excess, but I don't remember what it looked like. But I would be surprised if there was an effect. Yeah.
Other questions?
Thank you for your talk. This was super interesting. So maybe I missed it, but so the percentage of binarity is higher for Herbigs compared to T Tauris, or is it the same?
I didn't tell you, so you didn't miss it.
Okay.
Yeah, no, I know. Yeah, so Jonathan did look at the T Tauris, and I forgot it.
Because my question was related to it, because we know that the presence of a second star can truncate the disk.
Oh yeah, like T Tauri itself, right?
Yeah,
That's
so
true, yeah.
my question is, if there is a larger percentage of binarity for Herbigs, could this explain the larger accretion rates if the disk is heavily truncated by a
Yeah, I have
companion
to come back to the previous question. I think for the T Tauri stars, they are typically at 100 parsec. No, it's just they're typically at 100 parsec. Well, the Herbig stars, that's why I was doing this, are typically further away. So a 0.1 arc second separation is a completely different separation for T Tauri stars than for Herbig stars. So the fact that stars would affect each other, that we see that with the binarities that we trace, are much larger for T Tauri stars, simply because trace closer binary systems.
Okay, thank you.
Yeah.
And then I had another question. So you were showing the disk images with the spirals,
Yeah.
and you said that that would be a strong hint for planets being present. But if I recall, of course, there's many effects that can cause substructures within disks. I think one of them that's very important is also the presence of the magnetic field. So is it because a lot of them probably lack one, that the spiral structure is very indicative of a planet, or am I misremembering the mechanisms that can cause this?
Okay, so there's two things. We observe magnetic fields only in 10% of the Herbig stars. But we do find evidence for magnetospheric accretion in many A stars. Then you could say, well, that's a contradiction in terms. But if I have a complex magnetic field, then it averages out, and I might not be able to detect a magnetic field. So yes, if I'm looking at A stars here, they could well have a magnetic field. This guy is a B9 star, I believe. Not a detected magnetic field. And I don't think I had used any brain power to think about this, but I think it's a very interesting point, yeah. So essentially what you want to see is there a trend of structure with spectral type? And that might actually help us a little bit. Perhaps the sample is too small yet to do that type of thing, but yeah.
Okay, thank you.
Yeah. A lot of words for a non-answer.
Just a short question, Rene. Maybe I also missed it, but how can you so easily get accretion rates from UV luminosity?
Well, I dropped this chalk.
Yes, I know. This is where I started thinking.
So it's not easy at all, to be honest. But the premise, the underlying thought is really that material that falls onto a star will be radiated in UV. Now, for T Tauri stars, it's actually quite easy because T Tauri stars are cool. So anything that you see in the ultraviolet is most likely to be the accretion luminosity. But actually, to measure it in B stars that have a lot of UV emission themselves is not trivial whatsoever. John Vallum spent a year of his life basically trying to measure that. From the luminosity, if you don't have the mass and the radius, you can do something. But the slide I skipped was this one. We actually find a strong correlation between H-alpha emission, for example, the H-alpha flux, and the accretion luminosity. So a poor man's way of determining an accretion luminosity could be just to measure the H-alpha flux. There is no reason to believe that H-alpha emission is due to accretion, because it could be from the disk, but it works.
And so there's a kind of a parallel relation then between the accretion luminosity and accretion rate?
Yeah.
Yes.
Yeah.
Okay.
Yeah.
Yeah.
Gravitational potential energy, GM over R. Yeah.
Yeah. Yeah. Okay, good.
I had a question about boundary layer accretion. We're doing a project on the Herbigs. We wrote the email.
Hello.
Very useful talk. We struggle to find information about boundary layer accretion. So are there any observables you would expect to see? Like, there is more information on the magnetospheric accretion, so we know what to look for that, but is there anything we could see in the spectra for boundary layer accretion?
Well, I'd love to talk to you for half an hour. One of the things that we found, if you just play around with equations, is that you get less luminosity from a boundary layer. If I would look at the energy that's being released by dropping this chalk onto the Earth, that's much more than if I just basically am rotating Keplerian and I'm slowing down a little bit. So the nature of the ultraviolet excess would be different. You would actually get a slightly cooler measure. It's a little bit more complicated than that, but so we, or Ignacio Mendicotia, has been trying to get Hubble Space Telescope time to measure that, and then they said, why don't you use Swift? Then we applied to Swift, and they said, why don't you use Hubble? But that's the thing. Other measures that you could hope to think of is line profiles, but it's a little bit of a mess, these objects. So there's nothing that's really clear-cut as a smoking gun.
I think given the time, we're going to stop with the questions here, but I think Rene will still be around a bit, so you can try to catch him or maybe take him to lunch or something. I don't know if you already made plans.
At 2 o'clock. So, yeah.
Yes, so you can still find Rene around in the Institute, so let's thank Rene again for this nice talk.
Thank you for the many questions. That was lovely. Thank you.